Welcome to the RETScreen 13 course, Hands-on Assignment 1 on Residential Scale Grid-Connected Solar Photovoltaics. In this tutorial, we will build a RETScreen case study based on a solar PV study for a college in California. The initial study has been provided in the course, but the data has been updated to the context of 2012 and adapted for a residential system size of approximately 17 kilowatts located in Ojai, California. The PV system will be installed on a carport presumed to be located in a college campus setting and that can also be used to recharge electric vehicles. To begin, let's open RETScreen 4 and fill out the Start worksheet. In the Prepared By cell, type your own name. For this type of project and any project related to electricity production, we will select Power as the project type and PV as the technology type, since it is the technology commonly used in residential or commercial scale projects. Of the 5 grid type options, we will select a central grid and internal load option, since our project will be a grid-connected project and will be feeding at least a portion of its electricity directly to the load. In order to use the more advanced cost and financial analysis functions of RETScreen, we should select a Method 2 analysis type. We will also select higher heating value because the project is located in North America. In order to pick the most appropriate location, let's look at a map of the campus at Thatcher School. Referring to the Google Earth map shown here, we can see that the project site is located in Ojai, California, at a latitude of 34.46 degrees north and a longitude of negative 119.18 degrees east. Let's look at a map from the RETScreen Plus, which is a performance monitoring tool that offers maps not available in RETScreen 4. As we can see, Ojai has been added to the map, and the Oxnard Airport and Camarillo are the closest options. Let's select the RETScreen climate data location. After selecting the United States as the country, we are offered a number of climate data locations. We then select California as the state and Camarillo as our weather station to get the annual and monthly climate data shown here. We get the following data. The general area around the project site is around 12,000 square kilometers and features mountainous and desert-like conditions. Compared to coastal areas in Southern California, inland areas tend to offer an increase in elevation, solar radiation, wind and temperature levels, and a decrease in relative humidity. The effects of higher temperatures on PV system performance should be easily offset by high winds, resulting in an expected increased performance of at least 1%. Another key difference between coastal and inland sites is that coastal areas typically receive a great deal of morning fog, which reduces solar radiation levels. As a result, inland sites might receive an additional 9% more radiation than those in coastal areas. Hence, we can expect around an overall 10% increase in the number of kilowatt hours produced by an inland system compared to a system on the coast. For a more specific site selection, we still will assume that the PV system will be installed in close proximity to the campus buildings in one of the parking lots. This presents a unique opportunity to utilize existing developed space and may allow the arrays to provide shelter for vehicles in the parking lot. Let's now consider the solar carport application we will be using for this project. Solar carports are a unique application for solar PV projects that offer multiple benefits, including utilization of pre-developed space, easy provision of additional capacity to projects that are constrained for space, shelter from weather elements such as heat and rain, and increased comfort to occupants who do not use air conditioning. Similar to buildings, they maintain their value over longer periods of time and appreciate as property values increase. Solar carports also provide easier access to PV panels for any required cleaning or maintenance than roof installations, and can be placed in unshaded areas. From an installation perspective, pre-assembled kits can be delivered and mounted faster than virtually any roof structures and cables can be pre-wired on the structural elements of the frame, reducing the cost of on-site electrical work. When considered for lighting purposes, a base case credit could also be attributed to relevant projects. Finally, solar carports can easily be converted into electric car recharging stations and provide an additional source of income through sales of electricity to vehicle owners. Today, there are many solar manufacturers of carports and a growing number of carports specifically designed for solar. Let's consider a specific technology from a reputable manufacturer, a California-based company that offers prefabricated carports. Let's assume 3 Orion carport units will be installed for a total capacity of around 15 kilowatts. We will now proceed to the load and network analysis. A small residential application in California will typically have monthly loads between 300 to 600 kilowatt hours per month, with a corresponding gross average load of 1 to 3 kilowatts. The chart shown here, taken from a study on the impact of distributed energy efficiency with solar on-peak load, gives us a better idea of the average residential demand peaks in California. Based on these charts, we will assume gross average loads as shown here, and enter these into the corresponding cells. The system peak electricity load over max monthly average cell is used to enter the system peak electricity load over max monthly average load for the base case power system. This represents the percentage that the peak electricity load exceeds the maximum monthly average power load over the 12-month period. For this, let's input a value of 80%, which corresponds to 2.5 kilowatts over an annual peak load of 4.5 kilowatts, which is expected for this project. The electricity rate base case cell is used to enter the average electricity rate for the base case power system. In recent years, California electricity prices have been estimated in the range of 13 to 15 cents per kilowatt hour for major utilities around the state. For 2013, let's use an estimate of 14.5 cents per kilowatt hour, adjusted with an 8% increase, which has been announced for the period considered as the project start. This gives us a rate of 15.7 cents per kilowatt hour, which we will put into the electricity rate base case cell. At this point, RETScreen generates a load graph to display the energy demand patterns. Here we also have the option to enter in a value for energy efficiency measures for the proposed case scenario. By implementing such measures, the proposed case graph on the right would change accordingly. As energy conservation and efficiency measures can be implemented at minimal cost for maximum results and would reduce the load and allow more electricity exports to the grid, we will assume that energy efficiency measures would be implemented for this project. Examples of energy efficiency measures that could be implemented might include lighting, appliance upgrades, efficient windows, passive solar design, and efficient cooling system upgrades. Altogether, these can be expected to result in a 30% decrease in energy use. Our completed load and network sheet should now resemble the one shown here. Let's move on to the energy model. Because this is a detailed residential scale project analysis, for analysis type, we will use the Method 2 option for the energy model. Let's consider the solar resource assessment. While California generally offers a fair amount of direct solar radiation, climatic factors will likely influence the energy output. Such influences might come from local fog, dust, dirt, cloud cover, humidity, wind speed, and other microclimatic factors at the specific project site. While it is good to be aware of such influences, calculating the effects of these is quite complex and is outside the scope of this analysis. For this project, we will utilize the solar radiation data from RETScreen. Referring to the solar radiation map shown here, we see that at around 6 to 6.5 kilowatt hours per meter squared per day, the solar energy source near the project site is attractive for a residential PV system. This is about 25% higher than the 4.97 kilowatt hours per meter squared per day provided by RETScreen for the Santa Barbara weather station, but we will go with the RETScreen data, keeping in mind that this is a more pessimistic value. Next, we will select the type of sun tracking device used to mount the solar collector. The options from the drop-down list are fixed, 1-axis, 2-axis, and azimuth. If the solar collector is mounted on a fixed structure, we might select fixed. The remaining choices may be selected if the solar collector is mounted on a tracker. A tracker is a device that supports the solar collector and moves it in a prescribed way to minimize the angle of incidence of beam radiation on the collector's surface, thus maximizing incident beam radiation. Available solar tracker options include 1-axis trackers, which track the sun by rotating around an axis located in the plane of the collector, azimuth trackers, which have a fixed slope and rotate about a vertical axis, and 2-axis trackers, which continuously position their surface normal to the beams of the sun by rotating about 2 axes. For this case study, we will begin by selecting a fixed axis tracking scenario. Later, we will explore a dual-axis tracker option to assess the potential for greater energy production. For the slope, we will enter the angle between the solar collector, or the tracking axis, and the horizontal in degrees. Depending upon the goal of the system, it may be oriented for maximum yearly production, summer use, winter use, reduced capital cost, or for integration into the building architecture. Because this is a unique residential project aiming to generate the most energy and revenues possible year-round, for a fixed system, we will select a slope that is equal to the absolute value of the latitude at the project site. Several RETScreen simulations indicate that 30 degrees will result in a higher energy production. This is also close to our latitude value, so we will use it as our slope. The azimuth cell is used to enter the angle between the projection on a horizontal plane of the normal to the surface and the local meridian, with 0 due south. The preferred orientation should be facing the equator, in which case the azimuth angle is 0 degrees in the northern hemisphere and 108 degrees in the southern hemisphere. Note that the azimuth must be entered with respect to true south and not magnetic south. Compasses point to magnetic south, and azimuth directions based on this measure must be adjusted for the magnetic declination. Looking at the magnetic declination map shown, we can identify that Southern California has a magnetic declination of about 12.5 degrees west. So if the compass indicated 45 degrees west, the azimuth entered in RETScreen would be the difference between the two, or 32.5 degrees west. It is also important to note that the magnetic declination changes every year, so realistically we would want to look at the average magnetic declination over the project life cycle, but since this is a preliminary study, the calculated azimuth angle will suffice. The electricity export rate cell is used to enter the electricity export rate for each month, which is the rate paid by the electric utility or another customer. For the initial electricity export rate, we will use a value that is equivalent to the energy savings we will realize through on-site energy production. We will use the same value in the base case as the proposed case, which was defined in the load and network worksheet under electricity rate base case. For this, we will type the formula shown and copy this to all the other cells for the balance of the year. Next, we will pick the solar module. As the result of a more detailed feasibility, we could do a more in-depth analysis of the module options, but since this is a preliminary study, we will pick a module from a well-established manufacturer and that is popular for that type of PV application. The photovoltaic type cell is used to select the type of PV module considered for the application. The 7 options from the drop-down list are monosilicon, polysilicon, amorphous silicon, cadmium telluride, CIS, spherical silicon, and other. The PV module type selected will depend on a number of factors including price from suppliers, product availability, warranties, efficiencies, and related factors. Historically, monocrystalline modules have had the highest efficiencies but have also been so far the most costly. In recent years, polycrystalline modules efficiencies have progressed to approach the efficiency levels of monocrystalline and can usually be obtained at a cheaper price. Here we can see the progression of various photovoltaic cell efficiencies over the years. Thin film modules have typically had the lowest cell efficiencies but at the lowest price, while crystalline modules are the most common types of PV panel type. On the other hand, some thin film technologies have real-life performance advantages over low to mid-efficiency crystalline technologies in areas with more diffuse light and higher temperatures, as they are less sensitive to such lighting conditions and thermal losses than crystalline technologies. Hence, there is a case to be made for thin film when diffuse light and temperature are critical factors, or crystalline when energy density is a top criterion. However, it can be dangerous to make general assumptions, and RETScreen is an excellent decision-making tool to evaluate which solution offers the best financial returns. Let's consider SunPower Corp, based out of San Jose, California, as our panel provider. They claim to offer the most efficient and reliable solar panels and systems available today. Using the link See Product Database to the right of the photovoltaic area, select SunPower as the manufacturer and then the specific panel information shown here. The power capacity cell is used to enter the power capacity. For projects with an internal load, the percentage of the power capacity over the proposed case power system peak load is calculated. Before we input the official system capacity, let's consider the implications of capacity in the context of this project. We need to think about the cost-benefit relationship associated with a system that generates more electricity than required by the building and electric vehicle loads. Since we will be using net metering, we will have the option to receive monetary compensation for excess generation at the end of the year. Thus, we will want a system that is large enough to produce at least a little more than our total energy needs. Lower costs can easily be obtained thanks to economies of scale such as system aggregation, and with solar carports, we can also expect to see a reduction in labor costs compared to the average rooftop PV system. In order to make this project more viable, the system capacity should exceed the residential load plus the load attributable to 1 or 2 electric vehicles over the next 25 years. At 2.5 kilowatts average capacities per electric vehicle, and 8 kilowatts for the potentially higher future residential loads, we would be at 13 kilowatts, which is the minimum before we get significant gains from the electricity exports. So we will initially size the system at 15 kilowatts, which will require 3 Orion carport structures. Let's use the RETScreen product database by clicking on the link called See Product Database. Assuming 15 kilowatts, we will need at least 46 units, which will give a similar capacity of 14.72 kilowatts. We can go to the product database, which shows the energy output and other technical information as illustrated here, to make this adjustment. After inputting the select panel and 46 units, RETScreen calculates our capacity at 14.72 kilowatts. The efficiency cell is used to enter the nominal efficiency of the PV module under consideration, and module efficiency depends primarily on the type of cell used. However, within each of these categories, there are wide variations from manufacturer to manufacturer, depending on the manufacturing processes used. Having selected the SunPower panels, we can see that RETScreen automatically inputs an efficiency of 19.6%. Note that PV modules produced after 2012 are likely more efficient than what is indicated in the RETScreen database. For example, while 15% is a common efficiency for crystalline panels, many new modules provide efficiencies above 16%. For SunPower, the current manufactured data indicates a cell efficiency of 22.5% and a module efficiency of 20.1%. It is important to understand that increasing the efficiency manually in RETScreen would not result in any change. One way to account for this would be to change the type to Other, and then to change the temperature coefficient. The SunPower specifications provide a value of 0.38 for the temperature coefficient. Making this adjustment results in an increased production of 2,619 kilowatt hours and corresponds to over $400 more revenue per year. The miscellaneous losses cell is used to enter array losses from miscellaneous sources not taken into account elsewhere in the model. This includes, for example, losses due to the presence of dirt or snow on the modules, or mismatch and wiring losses. Typical values range from a few percent to 15%. Detailed loss estimates are generally performed as part of finalized system design. For our purposes, we will select a low value of around 1%, which should be appropriate considering the fact that there is no snow to deal with, no significant dirt, such as in urban environments, and the panels can easily be cleaned. Let's now consider the inverter characteristics. The efficiency cell is used to enter the efficiency, expressed in percent, of the electronic devices used to transform the DC output to AC. Values between 80 and 95% used to be typical for older inverters made in previous decades, but modern inverters have much higher rated efficiencies of up to 97 or 98%, sometimes even at 99% for quality large-scale utility inverters. For this residential scale project, we will assume an inverter with a rated efficiency of 98%. The capacity cell is used to enter the inverter capacity in kilowatts AC. This value is based on the power capacity and the inverter efficiency. For this project, considering the PV capacity, we will initially input 15 kilowatts. The inverter miscellaneous losses cell is used to enter power conditioning losses, if any, not taken into account elsewhere. At this early stage of project analysis, we can leave this value at 0. We can see that the capacity factor calculated by RETScreen in this context is 23.2%. In other words, on average, the system produces energy 23.2% of the time, or almost 8.5 hours per day equivalent. The electricity delivered to load is 11,205 megawatt hours per year, which means that we factor that just over 11 gigawatt hours per year will be used by the building and electric vehicles. The excess production is the electricity exported to grid calculated at 18,743 megawatt hours. The electricity rate proposed case cell is used to enter the electricity rate for the proposed case system, which represents the rate paid for electricity delivered by the utility after the implementation of the proposed project. This we know is equal to $157 per megawatt hour, so we can enter the following formula to carry that value over from the load and network model. The Select Operating Strategy cell is used to select the operating strategy from the drop-down list. For full power capacity output, by default, RETScreen assumes that the system operates at full capacity output. For power load following, the model assumes that the system is operating at a capacity to match the power load. In the context of this project, it is more advantageous to use the full output as the energy source is solar, which has marginal operating costs and provides for an excess of $2,935 compared to the power load following option. After completing the energy model, we get the following data in RETScreen. Let's now go to the cost analysis section. The capital cost of a PV system is composed of the PV module cost and the balance of system or BOS cost. The PV module is the interconnected array of PV cells, and its cost is determined by raw material costs such as silicon prices, cell processing, manufacturing, and module assembly costs. The BOS costs include such items as the cost of the structural system, electrical system costs, and the battery or other storage system costs in the case of off-grid applications. While the analysis of project costs for solar PV can be very detailed, the approach used here is a simplified one. The cost indicators that are most relevant for our purposes are the equipment costs pertaining to the items mentioned previously and the total installed project cost, which includes both hard and soft costs. In terms of fluctuations in cost data, the balance of capital costs in total project costs tends to vary even more widely than power generation equipment costs, as it is often based on significant local content, which depends on the cost structure where the project is being developed. Total installed costs can therefore vary significantly by project, country, and region, depending on a wide range of factors. The diagram from the IRENA cost study shown here illustrates the process and allocation of costs influencing PV projects. As we can see from this image, the cost of PV project equipment has been coming down significantly, especially in the years before 2012. This chart from 2012, which illustrates how the installed cost per peak watt decreases as the project increases in size, and this chart indicates that modules tend to make up the bulk of the costs. To understand the effects of economies of scale, we can consider residential scale projects, which cost almost 30% more compared to single-axis utility scale projects between the years of 2010 to 2011. In the table shown here, we can see that in 2010, residential projects had an installed cost of around $5.72 per peak watt. A project of this size in 2012 can be expected to achieve cheaper pricing at around $3.5 to $5 per peak watt. For our cost analysis, we will use method 1, as this is detailed enough for a first approximation, especially for small-scale PV projects. Method 1 presents us with the following breakdown. Once a potential cost-effective proposed case project has been identified through the RETScreen pre-feasibility analysis, a more detailed feasibility analysis study is often required. While medium and large-scale projects will often call for detailed feasibility studies, small-scale projects, such as the one we are considering, rarely merit the level of detailed analysis typical of such studies. Occasionally, very small projects may warrant feasibility studies, but this project is believed to be fairly straightforward in terms of the parameters. Likely, related feasibility activities would be handled in-house by the select system installer. Thus, we will not allocate any costs for a feasibility study for this project. Once the proposed case project has been identified through the feasibility study, project development activities follow. For some projects, the feasibility study, development, and engineering activities might proceed in parallel, depending upon the risk and return acceptable to the project proponent. Similar to requirements for feasibility analysis, development activities are much more pertinent with larger projects that require a number of non-construction related managerial activities. For a smaller project, such as the one considered here, the development cost may be reduced to the building permit. As an example, Los Angeles County lowered their residential fees in the summer of 2009 from $1,144 to a fixed fee of $370. The 2005 Sierra Club PV permit fee report for residential projects recommended a fixed fee of no more than $300, as this enables cost recovery for a city that has expertise in processing permits. The 2009 Sierra Club report shows $325 for residential PV project permitting fees in Southern California. Thus, we will assume a combined development fee of $1,000 to factor in potential permitting costs and labor. The engineering phase includes costs for the proposed case project site and building design, mechanical design, electrical design, civil design, tenders and contracting, and construction supervision. If the project is awarded on a design-build basis, then all of these costs would be included in the prices provided by the equipment supplier or contractor responsible for the project. If the project is awarded by tender based on specifications prepared by a consultant, then there will be engineering charges from the consultant overseeing the projects and perhaps the equipment supplier. We will assume that engineering will be handled by the system installer and included in the total installation price. Thus, we will not include any specific cost here. Using 20 cents per peak watt as our estimate for total estimated engineering costs, we would have a total cost of $3,000. The power system cell is used to enter the installed cost per unit capacity for the proposed case power equipment. The capacity is copied automatically from the energy model worksheet to the cost analysis worksheet. Typically, due to economies of scale, larger capacities lower the installed cost per unit of capacity. In Q4 of 2011, SunPower module costs were sitting at $1.46 per peak watt, with an efficiency adjusted cost at $1.08 per peak watt. This contrasts sharply compared to Chinese manufacturer prices at the time, which were estimated at 80 to 90 cents per peak watt, and Western manufacturer prices at 95 cents per peak watt. In 2012, SunPower expected to trim its efficiency-adjusted production cost to 86 cents per peak watt by Q4. We will assume that the SunPower modules considered would have a selling cost in 2013 above the expected price of 86 cents and instead use $900 per peak kilowatt. Note that while RETScreen refers to this as the base load, and that capacity actually serves as both base and peak load in the context of this grid-connected project. An access road for construction and an ongoing service road are normally required for a medium to large-scale power project. Since this is a small project being developed on an established site, no road construction is expected to be needed. The transmission line cost is site-specific and depends on the length, type, voltage, and location of the line, and the installed capacity of the power plant being developed. This cell is used to enter the length of the transmission line and the cost per unit of length. For a parking lot, to run the cable underground in a conduit, the average cost is about $18 per linear foot, or around $59,000 per kilometer. Considering a distance of 30 meters, or 98.45 feet, between the carport and the grid connection point, we will allocate $1,770. The substation cost is site-specific and depends primarily on the voltage and the installed capacity of the power plant being developed. For a small residential or commercial scale project, there is no need for a substation. The energy efficiency measure cell is used to enter the total installed cost for any additional power-related energy efficiency measures for the project. As an example, in Canada in 2006, implementing power-related energy efficiency measures to reduce a base case power system's annual peak load by 10 to 20% cost around $1 per meter squared to $10 per meter squared of building space, depending on the measures implemented. For a house of 200 meters squared, this would be $200 to $2,000. Energy efficiency and conservation improvements are easier in California, where space heating needs are very low. Assuming the implementation of thermostats, measures with air conditioning, lighting, water heating, and considering the government incentives in place, we will assume that $1,000 will be appropriate to make the energy efficiency upgrades necessary to reduce the electricity load by 30%. For this study, we will assume 3 Orion prefabricated carport units. Each unit protects 2 cars and offers space for 29 meters squared of panels, which is plenty for the 46 modules we will need to achieve 14.72 kilowatts of capacity. 3 units could actually hold up to 86 modules for a total of 16.96 kilowatts of capacity. A RETScreen simulation shows that increasing the panels to use all space available actually increases the NPV by $12,500 and the IRR by 0.6%. So, we will assume full use of the carport space with 86 modules sheltering up to 6 cars underneath. The manufacturer has provided a quote of $6,701 per unit. We will assume a delivery cost of $800, which we will input in the next section. The formula used is 3 times 6,701, which gives a total cost of $20,103. This corresponds to an installed cost of $1.18 per peak watt, which is well above the cost of typical fixed support structures alone, but within the current 60 cents to $1.40 per peak watt range with installation time and material. Similar to land-based installation, the solar carport can reduce the installation time since there is no need for roof replacement, anchoring, waterproof ceiling, or structural consideration due to the added load of ballast systems. For specific civil engineering related work to installation of the carport, we will add 10 cents per peak watt for the cable trench and the foundation anchoring. This adds $1,696. The balance of system and miscellaneous costs for the proposed case project typically includes a number of items such as specific project costs, building and yard construction, spare parts, transportation, training and commissioning, contingencies, and interest during construction. When necessary, additional spare parts for the proposed case project have to be included in the project cost. The extent of the inventory required will depend on the type and reliability of the system, warranty, complexity of equipment at the site, transportation difficulty, and availability of off-the-shelf components. The cost of spare parts should normally be part of the equipment purchase price. The suppliers would need to be contacted in order to obtain prices or other information required for a more detailed feasibility study. For this project, one of the significant miscellaneous hardware costs would be for wires, but we have already included that in the transmission line costs. Since fixed array PV systems have no moving parts, spare parts are typically not needed as much as with other technologies. In the context of this project, we will only add $100 for additional screws and asphalt filler. Transportation costs for equipment and construction materials will vary widely depending upon the mode of transport available and the location of the project site. In many instances, the cost will depend on distance and be based on a volume weight formula. Cost to handle the material at the receiving end should be considered, and logistical control is also important. Shipping cost data suggest a range between 18 to 19 cents per peak watt for residential projects built between the years of 2010 and 2015. However, this project is located in Southern California, where the vast majority of the project equipment should be procured with relative ease. Also, considering that this project is closer to the range of commercial scale projects, we can expect an overall shipping cost at about half the lower range of residential projects. We will assume that transporting the 3 carport units from Orion to a site within California will cost $800, shipping the 86 PV modules will cost about $600, and miscellaneous cost of around $200. We will thus enter the formula 800 plus 600 plus 200 for a total of $1,600, which corresponds to 9.4 cents per peak watt. The costs associated with the training of equipment operators and maintenance personnel will depend on the size, technology, and complexity of the project, as well as the experience of the O&M staff. Commissioning is the last activity of the construction phase, consists of operating all the equipment to detect and fix any malfunctions and ensure that the plant functions as planned. Commissioning normally involves monitoring of the equipment and performance over a set period of time under typical operating conditions. For small systems, this cost will likely be insignificant. While a more detailed study would use a quote from the system installer, for this study we have assumed that the installation cost is included in the BOS cost. Since the carports are pre-assembled kits, installation can be done in a few hours, and we will assume that the PV modules can be snapped in place the same day. Hence, we will budget 2 installers for 1 day and another day of finishing for an estimated $1,200 at $400 a day for 3 days. Inverters transform the direct current electricity generated from the solar arrays into alternating current electricity, which is what the electric grid runs on, and are often the second largest expense after the PV modules. The 2 common inverter types are string inverters and central inverters. String inverters are more popular for smaller residential and commercial installations, and especially in scenarios where shade may be an issue. Central inverters are commonly used in larger projects and are generally cheaper on a dollars per peak watt basis. Because significant shading is not expected, and in order to reduce costs, for this project we have selected 1 or 2 central inverters to be located under the carports. Inverter pricing can vary widely depending on the type and capacity of the system, with prices for residential and commercial scale systems easily doubling the cost for large systems on a cost per watt basis. Prices can range from 20 cents per peak watt for large utility scale projects to almost $1.10 per peak watt for very small systems. Mid-size commercial scale inverters made by Chinese manufacturers and without import fees tend to fall in the range of 40 to 80 cents per peak watt. Purchasing one 17 kilowatt inverter will likely be less expensive than purchasing 2 smaller units. Therefore, we will assume a SMA Sunny Tri-Power 3-phase grid-tied inverter rated at 17 kilowatts and with an extended warranty for $600 covering up to 25 years. The expected price is $5,815 with free shipping, so we will enter $6,415 as the inverter cost. The allowance made for contingency cost depends on the level of accuracy of the cost estimates. Contingencies are estimated based on a user-selected percentage of the subtotal of all project costs, excluding interest during construction. Note that contingencies are incremental in the sense that they are derived from project costs, including any credits. It is certainly possible that the RETScreen user experienced with project development could estimate costs in the range of 5 to 40% of the total initial project costs. When projects require large amounts of metals, the biggest financial risks or opportunities may relate to fluctuations in commodity prices as well as interest rates. While this is a preliminary study, costs for this type of project typically are not expected to vary more than 10%. So this is what will be used as a contingency value. This cell is used to enter the interest rate and the length of construction in months, which represents the length of time between building or infrastructure construction, delivery of the equipment, and commissioning of the system. Interest during construction will vary depending on the duration of construction and the cost of money. The interest during construction is then calculated assuming the average debt over the project length in months is 50% of the subtotal of all project costs. For example, if $1 million worth of equipment must be financed over 12 months at an annual rate of 10%, the user should enter 10% as the interest rate during construction. This would bring the calculated interest cost during construction to $50,000. The cost of interest during construction typically varies between 3 and 15% of the project costs. In 2012, benchmark interest rates in the US were at an all-time low of 0.25%. And based on a typical developer credit record, an additional fee of about 2 points might be added for short-term working capital types of loans. Thus, we will assume an interest rate during construction at 2.25%. With an experienced installer, this 17 kilowatt solar system can easily be built within less than a week. On the other hand, there may be payments that need to be made in advance, such as retainers for project engineers, consultants, and solar equipment manufacturers. Thus, we will assume an extra 3 weeks for construction, bringing total construction time to 1 month. Overall, given the cost analysis, we get a total cost of $58,518, which corresponds to $3.45 per peak watt. This is cheaper than the initial estimate, which may be attributable to significantly cheaper panel prices than those accounted for in our initial estimate. The carport comes as the most significant cost category, making up around 1/3 of costs, and the modules represent close to 1/4 of the project costs. The parts and labor cost item summarizes the cost of spare parts and annual labor required for routine and emergency maintenance and operation of the proposed project. System operation typically includes monitoring, regular inspection of the system, snow, ice, and dirt removal, scheduled maintenance, and related tasks. Typically, the PV modules will last more than 25 years and will require minimal maintenance. An annual visual inspection is recommended to check for loose wires and structural integrity, and components such as the inverter should also be inspected on an annual basis since these are more susceptible to failure. If the inspection is done by the system owner, which is not uncommon for small systems, it will be more appropriate to use a lower value. Some sources estimate typical O&M costs for large-scale projects around 1.5 cents per kilowatt hour per year, and RETScreen suggests a range of $0 to $200. At 1.5 cents per kilowatt hour per year, we get an O&M cost of $168, which falls within the RETScreen cost range. Although this rate is typical of larger scale systems, we will use it assuming that paid technicians would conduct the annual inspection and may require travel and labor costs. A contingency allowance should be included to account for unforeseen annual expenses and will depend on the level of accuracy of the operation and maintenance cost estimate section. It is common to carry a contingency allowance for at least the replacement of the most expensive component subject to catastrophic failure. Considering the durability of PV systems, an annual contingency allowance of 1 to 5% is a reasonable approximation depending on the project site. Since the yearly O&M costs are quite low, we will consider a larger contingency value of 25%. At this rate, the O&M cost would increase to $210 per year. The periodic cost section is provided to allow the user to specify the periodic costs or credits associated with the operation of the system over the project life. Gray input cells are provided to allow the user to enter the name of a periodic cost or credit item. A periodic cost represents recurrent costs that must be included at regular intervals to maintain the project in working condition. The project may also be credited for periodic costs that would have incurred over the project life of the base case or conventional energy system. The user then selects cost or credit from the drop-down list in the unit column along with the year and unit costs in the subsequent columns. The periodic cost typically associated with this project would be the anticipated replacement of major components such as the inverters after the initial warranty of about 12 years. Since we have assumed that an extended warranty of up to 25 years would be purchased, we will leave that area of the periodic cost empty. Let's consider the end of project life. With this solar carport, 34% of the system costs are attributable to the carport itself, which will not only have a salvage value at the end of the project, but will also appreciate in value. On the other hand, the PV panels and inverters only represent 37% of the total project cost, and we can assume that this system could be used for another 25 years with upgrades of the panels and inverters. We will therefore assume that the system will retain 60% of its value at the end of 25 years. So let's set the end of project life to credit and enter a value equal to 60% of the initial cost, or $35,111. Now that we've completed the cost analysis, let's move on to the financial analysis. The fuel cost escalation rate cell is used to enter the fuel cost escalation rate, which is the projected annual average rate of increase in base case and proposed case fuel costs over the life of the project. This value has very little impact on our project, considering the fact that we are not comparing to a base case relying on fossil fuel, and since there is no backup generator involved. Just for reference, let's enter 3%. The inflation rate is the projected annual average rate of inflation over the life of the project. It is very difficult to predict long-term inflation rates for any country. Even armies of financial analysts at central banks cannot predict accurately more than a few months or years ahead. Many factors come into play, including national and international political, economic, and weather events. In the image shown, we can see recent trends in inflation in the US. Assuming fairly stable conditions and based on a simple extrapolation of recent trends, we will assume inflation to stay in the range of 2 to 3% over the next 25 years. We will use a moderate 3% even though there are many inflationary pressures ahead. The discount rate is used to discount future cash flows in order to obtain their present value. The rate generally viewed as being most appropriate is the weighted average cost of capital used by investors. An organization's cost of capital is not simply the interest rate that it must pay for long-term debt. Rather, cost of capital is a broad concept involving a blending of the costs of all sources of investment funds, both debt and equity. The discount rate to assess the financial viability of a project is sometimes called the hurdle rate, the cutoff rate, or the required rate of return. The RETScreen model uses the discount rate to calculate the annual life cycle savings. For example, North American electric utilities currently have been using discount rates ranging anywhere from 3 to 18%, with 6 to 11% being the most common values. The discount rate or required ROI also depends on the level of risk of the project, with riskier but more potentially profitable projects carrying higher discount rates. For private projects, the discount rate may be used as a reference for the average rate of return of other financial placements, such as the returns offered by retirement plans, government bonds, real estate, and portfolios of stocks or registered pension plans. Since the financial crisis of 2008, and considering the mediocre performance of traditional investments since that time, and the fact that this project is located in the US, which is a mature market, we will input a 5% discount rate to represent a modest level of risk and associated returns. The project life is the duration over which the financial viability of the project is evaluated. Depending on the circumstances, it can correspond to the life expectancy of the energy-related equipment, the term of the debt, or the duration of a power purchase agreement. The model can analyze project lives up to 50 years. The project life of a solar project is typically 20 to 25 years, but depending on the scale, type of equipment, and environment in which the project operates, could be as low as 15 years or even much higher. Projects operating in harsh environments may dictate a shorter life. In the context of our project, with easy access for maintenance, regular monitoring, etc., we can expect at least 25 years. We will later look at the impact of an extended project life of 50 years. Financial incentives are any contribution, grant, or subsidy that is paid for the initial cost of the project. In the model, the incentive is deemed not to be refundable and is treated as income during the development or construction year, year zero, for income tax purposes. Although there are tax incentives available for solar PV projects in California in 2013, we will not input any value into the incentive and grant cell, as this is a preliminary study and we want to get a sense of the financial viability of the project at the select location without the help of subsidies. The debt ratio corresponds to the financial leverage created for a project. The higher the debt ratio, the larger the financial leverage. The model uses the debt ratio to calculate the equity investment that is required to finance the project. For example, debt ratios typically range anywhere from 0 to 90%, with 50 to 90% being the most common. Increasing the debt ratio will increase the annual cost and global cost of the project, which increases the IRR on equity but reduces the payback and the IRR on assets. For this project, we will use a middle range value of 70%, which is common for this type of project. The debt interest rate is the annual rate of interest paid to the debt holder at the end of each year of the term of the debt. The model uses the debt interest rate to calculate the debt payments. For example, at a minimum, the debt interest rate will correspond to the yield of government bonds with the same term as the debt term. A premium is normally added to this rate to reflect the perceived risk of the project. For this, we can apply the same interest rate we use for interest on construction of 2.25%. This is in the range of 15-year fixed mortgage rates, which is an appropriate comparison for this residential scale project. The debt term is the number of years over which the debt is repaid. The debt term is equal to or shorter than the project life. Generally, the longer the term, the more the financial viability of an energy project improves. The model uses the debt term in the calculation of the debt payments and the yearly cash flows. The term of the debt normally falls within 1 to 25-year range and should not exceed the estimated project life. Commercial type of loans from banks typically do not exceed 8 to 12 years, but energy projects can be treated differently. In a way, these loans are more like mortgages, and therefore longer terms can be negotiated. Just like with the debt ratio, increasing the debt term will increase the annual cost and global cost of the project, and will increase the IRR on equity but reduce the payback and the IRR on assets. Assuming the project owner's ability to negotiate with the bank, we will assume a debt term on the higher end of this range of 12 years. Normally at this point, a tax analysis would be an appropriate component of a residential PV project for the U.S., as various tax incentives are available that can mean the difference between a project that is financially viable and one that is not. Unfortunately, RETScreen does not have the ability to account for a declining balance depreciation scenario, which would likely apply for this project, so this aspect of the tax analysis would have to be done separately. Thus, for this case study, we will not conduct a tax analysis. The electricity export escalation rate is the projected annual rate of increase in the electricity export rate over the life of the project. For this, we will select a value of 5%, which is likely a conservative estimate for the increase of electricity exports over the next 25 years. At this point, we get the financial results shown here for the 25-year scenario. Let's now look at the impact of varying the life cycle using the same financial parameters. A project more than 25 years would require higher warranty or insurance costs for the inverters. We will assume that the inverters would be replaced at year 25 and will be under warranty for the next 20 years. So we will consider a 45-year project life in the third scenario. Here we can see the impact of the life cycle changes. Typically, a longer life cycle significantly increases all the ratios considered. As we can see, the project financial indicators are all attractive under the various project life cycles considered. While 45 years would give us the most favorable results, 25 years is a more commonly used period, and we will use this as the base for the next part of the analysis. Let's consider a dual-axis tracker for the project. There are a number of dual-axis trackers available on the market for parking lots. Trackers usually make the most sense compared to fixed structures when land is inexpensive or cheap and when it is important to maximize the production on a given footprint. For this reason, they have been popular with high-performance solar modules and in open areas where shading is not an issue. Let's save this as a separate scenario by changing the project name. In the energy model, we will change the solar tracking mode to 2-axis. The additional cost for dual-axis trackers may vary from about 15 cents per watt to $1.40 per watt. Smaller systems of less than 1 kilowatt tend to see the largest gap between fixed and tracking system cost. In the case of our project, dual-axis trackers are estimated to cost around 16% more than the cost of the fixed structure. Let's rename the cell in the cost analysis titled Carport as dual-axis tracker Carport. And we will enter the formula shown to get $24,319 as the cost. We will also assume an additional $500 annual cost, so we will add a new row titled Tracker Maintenance in the annual cost section and input that cost. The financial analysis page now suggests the tracker has a better viability with an improved IRR, NPV, payback period, and benefit cost ratio. We can see from the RETScreen financial analysis that in either a fixed or tracker scenario, this project is attractive from a financial perspective. With returns more than 20%, many organizations or homeowners would likely choose to follow through with implementing such a project. While unsophisticated homeowners may make decisions mostly on the basis of payback below 5 to 6 years, people and investors who are educated about the life cycle benefits and lower associated risks compared to other long-term investments would likely see this type of project as an extremely desirable investment. We can see that at an average 15.7 cents per kilowatt hour, base case electricity prices in the region are high, and at 2013, prices for PV systems are financially viable before any incentives. Many sources indicate that PV is closing in on grid parity in various locations around the U.S., and this is more the case for larger residential projects when prices of grid electricity are not subsidized and higher than the national average. As the life cycle cost of energy continues to fall and electricity prices increase, we can expect the number of solar PV installations to grow in a number of states and regions around the world, leading to massive market developments in the residential sector in the years to come. Furthermore, tax incentives that are unique to the U.S. in the form of a 30% personal tax credit on initial equipment costs and other such potential incentives available to this project have not been accounted for and would likely also make a major difference. It is important to note that the RETScreen PV model was initially designed for off-grid and commercial or large-scale utility projects and is not optimized to take into account important aspects of a net metering project. As such, the model does not take into account the favorable fact that electricity is exported to the grid during peak hours when rates are the highest. For this reason, real-world economic performance is expected to be better than what is calculated by the RETScreen model.